Hi there. I'd like to discuss the Unimat 3 lathe you see here. More specifically, I'd like to discuss its motor and drive belts. So if you own one of these and intend to either make your own belts, replace your motor brushes, or repair your motor, then hopefully you'll find something of use here. First off, making your own polyurethane belts. Back in the 1970s, this Unimat was designed to run nitrile rubber O-rings as its drive belts. Here are the specifications for the first of the two larger section O-rings that were used as the main drive belts. From them, you'll see I've calculated the length of that belt as 215 millimeters. I find it interesting that it was significantly shorter than the polyurethane equivalent I'd make now. It must have been stretched further to fit. And here are the specifications for the second of the main drive belts. It is the longer one, but once again it's shorter than the polyurethane equivalent I'd make today. Lastly, these are the original specifications for the smallest O-ring drive belt that's used on the power feed accessory. Now in this image here, we have the belting I use today. Don't worry too much about the specification for the minimum pulley size it should be used on. It outperforms the original nitrile belts regardless of the fact that Unimat pulley diameters go down to a mere 19 millimeters. Note how I've chosen to use 5 millimeter belting. Some vendors are selling belts made from 3/16 of an inch, in other words 4.8 millimeter belting. While these do the job, in my opinion they provide less grip. So I'm recommending you choose the 5 millimeter belting, even though the original belts were just 3/16 of an inch. Here's how 5 millimeter belting sits in my pulley grooves. That large surface contact area equates to superior grip. Moving on now, forget performing complicated calculations with deductions for tension to work out your cutting lengths. Even trying to get an idea of what they should be by wrapping your belting around your pulleys is problematic because you need to stretch it just to get it to bed into the pulley grooves properly. I've arrived at 224 millimeters for my main shorter belt and 288 millimeters for my longer one, largely just by trial and error. Now I simply cut my belting automatically to these lengths without any further thought. Perhaps you may like to use these same figures as your own starting points. Then if you think one of your belts is either too tight or too loose for your personal taste, just add or subtract a few millimeters until you settle on your own ideal cutting length. Even though I'm specifying my lengths to the individual millimeter, it's really not that critical. The belts have a great deal of stretch and their length even changes during the butt welding process. By the way, I fitted a ready-made polyurethane belt to my power feed many years ago. I've never needed to replace that one and probably never will because that feed sees little use. If I were to want to make a replacement now, I'd need to buy a roll of smaller section belting and that would be cost prohibitive. It would likely be cheaper for me to buy at least 2 ready-made replacements instead. Here's the length of 5 millimeter belting I've just cut to make a new version of my longer main drive belt. A shaft craft knife works fine. I have a trigger-operated soldering gun and V-blocks to assist me in my butt welding, but you'll obviously need to make do with whatever you've got available. Here are the instructions I've set myself for the next time I have to do the job. Not having enough hands was a problem. At first I tried using a rubber band to hold down the trigger of my soldering iron, but I found that caused the element to become too hot. Also, without having that straight edge to push against, I was finding I couldn't align the ends before the plastic began to cool and set. By the way, the idea of using V-blocks isn't mine. Credit for that belongs to another YouTuber. Here's one of my new belts cooling down before being ready for use. I trimmed my butt welds with a pair of side cutters, but a craft knife would do the job just as well. And here are two new belts I've made freshly fitted. Here you see my pulleys pitch circle diameters for anyone who's interested in those. Of course, belt wear still occurs when running polyurethane belting. While performing this ambitious task of fluting a cast iron column recently, I suddenly noticed a sawdust-like material appearing. One of my drive belts was being shredded. I didn't take a photo straight away, but here's one I took some time later after I'd vacuumed up most of the mess. You can see a little of the debris still remains. Now to the subject of replacing the motor brushes. First, you need to remove your motor from your lathe. The pulley should slide off easily enough once this securing screw is removed. Then simply remove both motor mounting screws and the drive pin. By the way, the first time I removed this pin, I lightly sanded it to transform it from being a light press fit to an easy sliding fit. I strongly recommend you dismantle and clean your motor whenever you undertake brush replacement. Brush wear creates carbon dust. The motor is completely sealed, so this dust has no way of escaping. Furthermore, carbon is a good conductor of electricity, so the accumulation of this dust will encourage current to take short circuits. I learnt this the hard way. That is, from damage being incurred to my motor, but I'll discuss this in more detail later. If you have access to them, as we do here, then it is always good practice to remove the brushes before you attempt to open a motor. So that's what I've gone and done. You gain access to your brushes by removing the two plastic plugs. Here I am, having removed a plug after first having softened it with a hairdryer to try and make the task easier. And here's what lies beneath. Disconnect the spade terminal with a pair of needle nose pliers or similar, and use a piece of wire that's been bent to 90 degrees at one end to withdraw the spring off the base of the brush. Now simply pull up on the pigtail and the entire brush will come out. Here are my brushes after 30 odd years of use. Notice how one is almost like new, whereas the other is severely worn. I can develop theories as to why this has happened, but I've not settled on any of them just yet. And here's what's written on the side of my barely worn brush. When I look at eBay right now, I see one vendor attempting to rip people off by offering completely unsuitable replacement brushes, while all the others appear to be offering compatible brushes, but at very high prices. The task of obtaining our replacement brushes is made difficult by their unusual, almost square shape. But don't let this force you into paying silly prices. Instead, buy similar but wider brushes and then sand and file them to the correct specification for the Unimat. I went with buying 8x5x15 brushes that were designed to fit a Bosch angle grinder. Note, however, that no matter what you buy, the pigtails must be offset. Here I've sanded the two on the left down to the correct size. They started off being the same as the one on the right. Noticed also how I filed grooves for the springs to rest into. Now here's a picture I'd taken earlier when I was actually sanding one down. To finish them off, I used a piece of sandpaper wrapped around a socket to create the commutator's curvature at the point where they meet. I'm not entirely sure this last step was necessary, but I did it anyway. Here's my original barely worn Unimat brush on the left, whereas my completed replacements are on the right. Now let's continue with the dismantling process. As I've already said, the motor needs to be opened and cleaned. First, remove the two long screws that hold it together. The rear cover is relatively simple to disconnect and separate from the stator, but to separate the front one, you'd need to desolder wires. So I left the front one connected and tried to avoid disturbing it as much as possible. Here I am disconnecting the two spade terminals that'll allow the rear cover to be removed. I'm using surgical forceps for this job. And here's that rear cover successfully separated. At this point, I blew clouds of carbon off all the internal surfaces. I'm lucky enough to have a powerful air gun on hand, and I believe this is the only tool to use for suitably ridding these motors of the accumulated carbon deposits. And here's my rotor. The commutator needs to be cleaned with a light sanding, and the insulation between the commutator segments needs to be cut back to prevent it from hitting the brushes during rotation. Here's another close-up view. And here's a shot taken after some sanding work. Now we have another view of the rotor showing how the pulley will eventually be refitted. And here I am cutting back the insulation between the commutator segments. Now we have a shot taken after all my cutting and sanding work was completed. And here's my rotor alongside my rear cover. Now we're looking at the front of the motor, and now we're looking at the front of my stator windings. Reassembly is basically the reverse of the dismantling process. Bring the front cover up against the motor's main body and stator, ensuring the dowel pins enter their respective holes. Then slip the rotor inside after first making sure the thrust washers are present and in the same positions you found them in during disassembly. In my case, I had 3 on the rear and just 1 on the front, with them all being of varying thicknesses. When the rotor is installed, reconnect the 2 spade terminals onto the rear brush holder assembly. Refit the rear cover, lock it all together with the 2 long securing screws, and then fit your new brushes. Here's one of my new brushes installed in my motor. Incidentally, my thrust washers don't completely eliminate my end float, however I'm not worried about this. I measure my end float as being around 0.5 millimeter. By the way, I forgot to mention lubrication of the bronze rotor bushes. They don't need much. I simply add a drop of sewing machine oil to each one. Now let's move on to motor repair. I fell into the trap of ignoring maintenance work on my motor. So truth be known, I performed the already described brush replacement only after experiencing a motor problem. This problem occurred when my motor was under heavy load, and it revealed itself through a sudden loss of power accompanied by a whiff of smoke. My motor is fully sealed, so just imagine how much smoke must have been inside. So my first step at that time was to replace my brushes. After doing this, I then attempted to run my motor with its plastic brush caps removed so I could see what was happening inside. I both saw and heard severe electrical arcing occurring somewhere in the vicinity of my brushes. This then led me to discover the existence of an unwanted circuit between one brush and the body of my motor. I'd better add a safety warning here. This circuit was attempting to liven up the body of my motor to dangerous voltage levels. that is to 240 volts, which is the voltage available inside my home. I'm a qualified electrical service technician, so I know how to work safely. If you don't, leave this sort of work to those who do. That said, I'll continue. The resistance of this fault circuit wasn't low enough to blow my house fuse, so I continued to have power available at the socket beside the table my lathe rests on. Here I am discovering that short circuit. And here I am confirming the other brush is without any similar fault. Now this photo here shows how part of my plastic brush holder plate had been transformed into a solid chunk of carbon. I suspect my lack of maintenance had caused carbon dust to accumulate to the point where it had created a tracking path. The heat from this would then have converted the surrounding plastic to charcoal, thus exacerbating the problem. Here is my backing plate after I scraped that solid blob of charcoal away. At this time, I discovered further damage in the form of one leg having been blown off the nearby ceramic capacitor. And now here's that capacitor after I'd soldered in a replacement leg. This photo now shows how I filled the hole with hot melt glue. And now we're looking at that from the opposite side. And here's the repaired brush holder assembly reinstalled. I'm pleased to report this repair work has restored my motor to full performance. Now I'll show you some random pictures of machining work I've done using my Unimat. They're all related to my model stationary steam engine hobby. I'm hoping you may like to look at them while I drone on some more about two aspects of the Unimat motor. The first is its low power output. This is widely criticised, yet I believe it was deliberately chosen. This is a genuine mini lathe after all. As such, whether turning, milling or drilling, it's designed for cutting edges to be performing shallow cuts only. It's simply not robust enough to cope with heavy cutting duties. Forcing it to do so is likely to cause components to distort, mountings to work loose, increase wear, loss of machining accuracy and even breakages. So upping my motor power in conjunction with running tooth belts has never been an option for me. Having said this though, I've just followed the lead of others and adapted a 24 volt DC scooter motor to fit it. But then I felt forced into doing that, and the scooter motor is definitely designated as being the spare. You see, the recent failure of my Unimat motor taught me just how scarce and overpriced replacements are. Not only this, it taught me just how much I value this little lathe. I can't bear to be without it. My scooter motor utilises the same belt and pulley drive system, so it still has the inbuilt safety protection this offers. I'm referring to the fact that my drive system will automatically disconnect by slipping should anything untoward happen. On the rare occasions when a component has come loose from my chuck while machining, the tool is bitten in, the chuck is stalled, and I've simply reached over and turned the motor off. In contrast, such an event on a more powerful lathe is very dangerous indeed. I've got to admit though, the scooter motor has got me excited. Never before has my drive spindle been able to rotate backwards or rotate full power at absolutely any RPM I care to set a dial to. Apart from my desire to keep this machine looking original and to keep it capable of running its original motor, with the scooter motor fitted, there would be no reason at all not to simplify its drive system towards a single pair of pulleys with just one belt and just one belt position. I aim to show off my scooter motor setup in a video I hope to produce shortly. Just a quick word here about the motor's duty rating of 80%. This means simply that it should not be operated without due regard for its operating temperature. In other words, if you notice it's getting too hot to hold the palm of your hand against, you must stop using it immediately and go and do something else, like have a cup of coffee. The manufacturer thought they were explaining our obligations more clearly by talking about 2 minutes of off cycle for every 8 minutes of duty cycle, but really this statement merely increases misunderstandings. If the machine is performing light work, the motor might not need any time off at all, yet when it's under heavy cutting loads, it'll probably need 30 minutes of off cycle for every 8 minutes of duty cycle. The only thing to worry about here is your motor temperature. Here's a copy of the most important note on this subject within the operating manual. And here's the stupid note they wrote, and even added to the label on the motor, that's given so many people the mistaken idea that they can keep running an overheated motor provided they stick to the 8 minutes on and 2 minutes off rule.